Hello. Using my WPF application that I have created, because WPF is awesome, I shall be describing the RSA protocol in a little bit more mathematical detail. So, encryption is a wonderful thing, and it is what keeps the internet alive and sensitive data secure. So, how does it work? Well, one of the first asymmetric crypto system, and the one widely used today, is RSA, which was invented after getting drunk on Passover, after too much Manischewitz. The Jews. I'm a Jew, it's okay. RSA is a relatively slow encryption algorithm, so instead of directly encrypting user data, it's used to exchange a symmetric key. To use in a faster symmetric crypto system, for example, you're just putting your key into your message in order to, as you start, in order to start exchanging data with one another. And the advantage of using RSA is that, as an asymmetric crypto system, the receiver can broadcast a public key to anyone who wants him to send data, but once that data is encrypted, it is really difficult to decrypt without knowing the receiver's private key. So, say Alice wants to send a message to Bob. Well, Bob first has to create his own private key, and RSA works on modular arithmetic and on the premise that factoring very large numbers is extremely difficult for classical computers. So, well, I look like a math nerd with all these equations posted everywhere. Well, what if I am? Anyways, we can just get our two prime numbers. We'll just make two up. So let's say we have 11 and 13. We want to start by calculating n, which is very simply 11 times 13. Everything happened there, but what we can see up here is 11 times 13 is 143. We calculated that from our two primes. So this is a composite number made of the primes p and q. What we can do with n is use what our friend Euler has invented so long ago, the Euler-Totient function, which is up here at the top left. And if n is a product of two primes, then just so happens that the totient function is the product of one less each prime, so p minus 1 times q minus 1. And that would mean that the totient of n here is 10 times 12, which is 120. So from this totient function, we want to get two numbers. We want to get our public key and we want to get our private key. So E is the public key that is used for encryption. D is the private key that we use for decryption. Now, why we need these two keys is what we're going to do is we're going to create a message, for example, hello world. And this will be transformed into its ASCII representation here. And when we encrypt it, over here we're going to take the exponent of this, so 72 to the power of e, which is 11, and take that modulus n. And modulus just means we divide it by 143 and take the remainder of it. And say encrypted, we can see it's 72 to the power of 11 mod 143, just so happens to be 28. And that goes for all of these. Then once, in order to use this encryption, we transfer the ciphertext over to Bob. Bob decrypts it, and he gets hello world back. Now, what happened there? Well, what Bob did was he took the exponent of 28 to the power of d, which just also happens to be 11. It doesn't have to be the same number, but they do have to be specific numbers. And if e and d are chosen carefully, then since m to the power of e mod n to the power of d mod n is the same, because of modular arithmetic, is the same as m to the power of e times d mod n. And our friend Euler said that if e times d mod the totient of n 120 is equal to 1, then we get back our plaintext. So using the great totient function of yore, the amazing math that was created long ago to power our computers today, we're able to create keys that we can encrypt and decrypt on the other side. But in the middle, we have Eve, evil Eve, and evil Eve wants to steal our message. So what she does is she knows N, that Bob broadcasts that to everyone. So she wants to get P and Q. How did you make N? You made it with P and Q. So we factorize it, and we get P and Q. They're 11 and 13. Wow, that's crazy. Calculate the total of them, 120. Wow, we're getting all this information. Private key, 11. We cracked it. The key is 11, which was the same key as this. It's crazy. But now we can crack it, and we can see what Alice sent to Bob. That isn't good. We need a bigger, a stronger key. How about 50,461 times 18,217? How about that? We calculate the keys from them. That's our big token, that's our big N. I can just, there are a lot of different keys that we can use for this particular N. I can just shuffle them forth. Here we have public key of 353, private key of that number. And say Alice wants to ask, how are you? We encrypt that. That is the series of these numbers that we'll send over to Bob, who decrypts it and gets how are you. Eve, however, has to start factorizing all over again. It's not too hard. These primes are not that big. Calculate the token, calculate the private key. We crack it, we get how are you. We need bigger primes. How about we go to 49979 hold on, 693 67867 Great numbers. We get our keys from them. They're a little bit bigger. We encrypt. Cats are cool. Encrypt. We decrypt. We can see that we get the message, but can Eve get the message? Well, Eve has to start factorizing, can see P going up, and we're trying to find this prime P. We're trying to crack, we're going through all the possible numbers that it could be. Now, of course, this is not the fastest way to do it. This is extremely slow. And the fastest factorization algorithm known is the general number field sieve, which works in sub-exponential time, which is extremely fast. Here, we found the key, we found the prime P, we got Q, we got the token, we got the private key, we cracked it, we got cats are cool. We need bigger primes. So that's one prime. And this is our other prime. So we calculate the keys and we encrypt again, or high. We encrypt that, we decrypt on the other end, we get high. But to factorize, oh, that'll take a while. Well, this we'll sit here for a while. This won't be fast. So as I was talking, general number field sieve would be able to crack this key in less than a second on an Intel i7. This is going to take quite a few hours. However, it would take that algorithm would take an hour to crack a 260-bit key, which is, well, this is approximately 100 bits, and about 100 years on hundreds of server computers in order to crack a 2000-bit key, which is what is normally used. So, as this is a huge number, a 2000-bit key is about 20 times more digits than this, and it is relatively impossible to crack unless you use a quantum computer. Now, quantum computers are threatening to put an end to RSA's reign since the invention of Shor's algorithms for quantum computers, which leads to studies of crypto systems that are secure from quantum computers, and hopefully we can defend from those as well, lest they disintegrate our world of security. Thank you, and Eve is still living in the past.